Um, Good evening, everyone. This is the NPTEL problem solving session for the course Introduction to Robotics, and this is week 6. And last week we had discussed basics of DC motor, we had calculated torque for a given amount of current, and conversely, we had calculated current required for a given amount of torque. Um, and this week was more. This week's lectures were more into power electronics and more about DC motors, essentially. So since it was mostly theoretical and uh, calculation based, so we will do some problems directly, and I will walk you through, guys, these problems. Okay, so let us start with the first one. Yeah. Okay, so this is Introduction to Robotics, week 6, and this is problem 1 of the problem session. So I'll just read out the problem out loud for you. A DC motor has an armature resistance of 0.4 ohm. The back EMF constant of the motor is zero point 0.3. Okay. I am assuming that you guys by now know what is meant by armature resistance and the back EMF constant and all this stuff. The motor is connected to a fan blade whose okay, load characteristic is defined by 0.002 omega. I think it should be squared, right? Because load characteristics is, how your load changes with your, how the load on the motor, that is most of the times in form of a torque on the motor. The motor spin uh, varies with the RPM of the motor. Okay, so here we have been given that it varies with omega squared. Okay, so that's just what you have been given here. Okay, this omega 2 that is written here is essentially omega squared. Not essentially, it is actually omega squared. The armature terminals of the motor are energized from a buck DC to DC converter, okay, which is in turn fed from a 48-volt DC source. Okay, so I'm also assuming that you guys know from the lectures what a buck or what a boost converter is. Okay, if it is intended to operate the fan blades at a speed of 60 radian per second, okay, so we have been given the angular speed of the motor. Determine the on duration of the switch. Okay, like if the switching frequency is chosen to be 8 kilohertz, okay, what is the on duration? Okay, so basically we want the duty cycle of this PWM signal. Okay, so now let us write the solution. Okay, so let us first write all the quantities that are given to us. Okay, so what has been given? We have the armature resistance as 0.4 ohms, right? And we have the back EMF constant as 0.3 volt per radian per second, right? And then we have been given operating speed, that is 60. So it is already given to us in radians per second. We don't need to convert it anyhow, right? And yeah, load torque characteristic. Okay, P as a function of omega. Okay, what is this? We have seen above, it is 0.002 omega squared. Okay, so if I just quickly put my omega, given omega here, okay, it comes out to be points, so 7.2 Newton meter of torque. Okay, this is how much load is there on the motor for the given RPM. Okay, for the given operating speed of the motor. And from last week, right, we know that uh, the speed torque equation. Okay, speed torque equation of the motor. Okay, it is given by omega is V over K minus RA and the load divided by omega squared. No, K squared. This is omega, right? So this is from last week, last week's lectures. If you have any doubt, if you have any doubt on how we, sorry, if you have any doubt on how we got got this equation, you should refer to last week's lectures. Okay, so we now just substitute all these values that we have been given into this equation, okay, to get the voltage, okay, or the armature voltage, right? So armature voltage, okay, when you put everything here, it will come out to be 27.6 volts. Okay, you just have to, plug omega here, and let us say that this is, call it K. You put K here, okay. Again, you square K and you put it here, okay, and you put this RA, right, here, and this load torque that we have calculated here for this particular omega, you put it here, okay, and after you put all these things, okay, you'll get omega, you'll get V, okay, your armature voltage. So once we have the armature voltage, okay, what is the supply current that we have been given? We have been given that the supply voltage is 48 volt. Okay, basically, if you are using any power supply or you're using any battery, then the voltage of that power supply or battery is 48 volts. Okay, and since you know if this is the supply voltage and this is the actual armature voltage, okay, then the duty cycle for the step down converter that is being used, okay, we want to calculate it uh, of the switch, right, of the switch of the converter, okay. So what will be the duty cycle? We know that duty cycle is how the max for how much voltage is there divided by the maximum voltage, okay. So it comes out to be 0.575, right? So this is essentially how much time you have to keep your switch on for every given time step, okay, for every given sampling time, okay, or switching time, such that the net voltage that you see at the armature is 27.6 volts, okay. So basically, you should keep the switch on for 57.5% of the time, 50.5% of the switching time, okay. And what is the switching time that I'm talking about here? Okay, this is just 1 over my frequency, right? And what is the frequency that I've been given? I know that the frequency switching frequency that I've chosen here is 8 kilohertz. Okay, so time period is 1 over frequency. Okay, so it is 1 over 8000. Okay, so what is the duration? Okay, we have to calculate this. Okay, duration for which the switch is on. I told you, right, that if this is the total time, okay, total switching time, then this is the fraction of this time, okay, fraction of the switching time for which I should keep it on, right? So duration for which the switch is on, I call it TD, and this is just D times TS, 0.575 times 1 over 8000. Okay, and if you calculate, you should be able to verify that it comes out to be 71.875 microsecond. Okay, so this is the time for which the switch is on, okay, in one cycle, right? So I'll just walk through you guys again what happened, what we did in this question. We had been given some characteristics of the motors like the armature resistance, the speed, back EMF constant, and the operating speed, and we have been given the load torque characteristics of the motor. We have been asked, okay, what is the on duration of the switch? Okay, given the supply voltage, and we have been told that we are using a buck converter, okay, DC to DC buck converter to reduce the voltage, okay, to essentially control the current, control the voltage that we apply at the motor terminals. Okay, so we know that this on duration, it actually changes the net armature voltage of the motor. Okay, net armature voltage applied at the motor. Okay, so if I somehow calculate the armature voltage, then I can use that armature voltage and the net supply voltage to calculate the duty ratio. Okay, that what is the fraction of time for which my switch should be on for the net voltage to be 27.6 instead of the source voltage 48. Okay, now how do I calculate the armature voltage given all these quantities? I know from week 5 lectures that the speed and torque equation of the motor is given by this equation. Okay, so I've been given all these other quantities, okay, and I have to find V, right? Because I just told, right, that if we know V, we can use V to calculate the duty cycle, and we can use duty cycle to calculate the switching time, okay, or the time for which the switch is on, okay, given the duty cycle and the switching time. Okay, so we use this equation to calculate our armature voltage, and then similar thing that I have told you again. So I hope that this this problem is quite clear. So we'll move now to the next question. Okay, so I'll mark this as question number 2. So you guys can see this question, right? Yeah, I'm sorry. Okay, so I'll just quickly read out the question for you. A DC motor has a armature resistance of 0.5 ohms, okay, and an armature inductance of 1 millihenry. The back EMF constant of the motor is 0.5 volts per radian per second. Okay, so the motor is connected to a fan blade whose load characteristic. Okay, so this is essentially again the load characteristic for the motor, that is motor and the fan assembly. that has been given to us. Okay, because most of the time the load is due to the peripheries that are connected to the motor. Okay, in this omega squared relation, it is mostly in the case of fans or propellers, okay, that are connected to the motor. And the armature terminals of the motors are energized again similarly from a buck converter. Now the switching frequency of this buck converter has been given as 5 kilohertz. Okay, and we have been given that this is fed from a 100-volt DC source. Okay, so our source voltage, DC source voltage is 100 volts. Now uh, we want to determine the peak to peak value of ripple in armature current. Okay, when the fan blades are operating at 60 radian per second. Okay, so we want to know the peak to peak value of the ripple in the armature current, right? So let us solve this. Okay, so I'll just first write, what have been given to us already. So we have been given armature resistance as zero point 0.5 ohm. We have been given armature inductance as 1 millihenry. Okay, and the back EMF constant, that is zero point 0.5 volt per radian per second. Okay, and you have been given the operating speed of 60 radian per second. Okay, and your load torque characteristic is 0.002 omega squared. Okay, and this is similar to the last problem that we just did. Okay, and this we know that this turns out to be 7.2 Newton meter. Cool, no problem till here. Okay, so now what we need is we need the armature current. Okay, so okay, we'll calculate the armature current because to calculate the peak to peak ripple, okay, we will need the armature current. Okay, so we'll just calculate the armature current. Okay, and we know that armature current is given by this. Okay, because both the Ks are same for a DC motor. Okay, so this is your 7.2 over zero point 0.5. That gives me 14.4 amps of armature current. Okay, and also we will calculate the induced back EMF. Okay, yeah, and that is given by K omega. Okay, so zero point 0.5 times 60, and that is your 30 volts. I'm assuming that you guys are already comfortable with all these terms, armature current and the back EMF and the load torque on the motor. Okay, if not, then you should uh, go and watch previous week's lectures. Okay, so you see the speed torque characteristics of the DC motor. Okay, the speed torque characteristic. Okay, they are given as your V over K minus RA. This is your torque over K squared. Okay, now if you put all these given quantities here, okay, like whatever we have been given, like K, omega, RA, and T, we have already calculated the load torque and K squared, okay, you will get V as, 37.2 volts. Okay, okay, so if I compare to the last problem, the armature resistance is different here. Okay, that is why we are getting a different voltage. Okay, and what is the source voltage? This is the armature voltage. What is the source voltage that was given? 100 volts. Okay, so again, what is the duty cycle? That is 37.2 over 100. Okay, so this comes out to be 0.372, basically 37.2%. Okay, so my switch is on at every cycle, okay, at every time duration for my, when I flip, when I give signal to my switch, okay, I keep the switch on point for 37% of the time. Okay, this is what duty cycle essentially means, right? And now the switching period, okay. So what is this 37% of the time? Okay, like in seconds that I'm talking about. So for that, I need to first calculate the switching frequency, and that is my like 1 over Fs, right? So the time for which it is on, okay, this is given by d times ts. Okay, so 0.372 times 1 over 5000. Okay, and that comes out to be, okay, uh, that will come out to be your a, yeah, I guess, yeah, I just wait. Okay, uh, so there's a 37.2 divided by 5. Okay, so 7.44. So this is my 74.4 microsecond. Okay, this is the time for which it is on. Okay, and now what I actually want in this problem is the peak to peak value of the ripple current. Okay, basically ripple in the armature current. Okay, and how is the ripple in the armature current given? So ripple in the armature current is given by this equation, right? Vg minus the armature current times phase voltage, oh, phase current times phase resistance minus EB divided by the inductance times the on time, right? Because this is the time for which it was on, and this is what creates the ripple. Okay, so when you substitute, now you have everything. Okay, you have your VG, okay, that is your ground or the source voltage. You have your I, okay, that is your armature current, IA. Okay, I should, use the same symbols that I had used above. Hmm. Yeah, so this is my armature current. This is my back EMF. This also I've calculated. This is the armature inductance. I've been given this and this D times TS, basically my on time for the switch. I've just calculated it. So you put all these values here, okay? And what we will get finally after just doing the small amount of after doing these calculations is that the peak to peak value of the ripple in the armature current is 4.672 amperes. Okay, so like this question, in some sense, you can say that it was an extension of the last question. Okay, so in last question, we had determined that for how much time is the switch on. Okay, and here we have actually used, okay, how much time was the switch on, that is our TD, for calculating the ripple in the armature current. Okay, cool. So I'll move on to the next problem. Okay, this problem is related to H bridge converter that you have studied this week. Okay, so I will just quickly go through the problem again. Okay, uh, mhm. So a permanent magnet DC motor is supplied from a H bridge DC to DC converter. Okay, so we are not using the buck converter now. Okay, and the input voltage to the converter is 48 volts, and the switches of the converter are numbered as followed. 1 and 4 refer to the top and bottom switches of the first leg. 3 and 2 refer to the top and bottom switches of the second leg. Okay, switches 1 and 2 are operated together, and 3 and 4 are operated together. Okay, the gating pulses to the switches, okay, basically the gates of all these switches are derived by PWM operation by comparing the reference voltage. Okay, so there is just a lot of terminology here. We'll go slowly. Okay, basically the switches are being controlled by a PWM signal. Okay, and how the PWM signal is being generated? It is being generated by comparing the reference voltage with a bipolar triangular waveform of frequency 10 kilohertz and amplitude 10 kilovolt. Okay, so essentially what it wants to say is we have a bipolar triangular waveform, right? So a bipolar triangular waveform is a waveform like this. Okay, and it is saying that we are using this. Okay, basically we are comparing our reference voltage. Okay, uh, right, comparing our reference voltage to the voltages here. Okay, this has been given 10 volt. Okay, and the frequency of this bipolar triangular waveform, okay, it is given to us as 10 kilohertz. Okay, so what this wants to say is that this is just a mechanism, okay, of how we generate PWM signals. Okay, so we get this kind of timing signal from our microcontroller. Okay, so in microcontrollers there are timers that help us generate waveforms like this. Okay, that and then we can set the reference voltage, okay, to get signals, okay, whenever that particular voltage is reached, okay, in this kind of timing signal. Okay, so essentially this gives us uh, an idea of the time period. Okay, like we already have the idea of the time period, so when we compare essentially when we got the signal, okay, or at what voltage we got the signal, we can actually generate the, we can turn any switch on or off based on when we got these signals. Okay, so based on our reference signals, we can turn these on or off. Okay, so yeah, that is the whole point why we have been given, okay, that what kind of signal is being used to generate the PWM waveform. Okay, and then we have been given some things about the motor. Okay, that the armature resistance is 0.4 ohm and the speed wave constant is, or the back EMF constant is 0.25, and the constant load. Okay, yeah, so again here we have a constant load that has been given to us. Okay, it is driven by the motor while operating at, what is the angular frequency or the rotation angular speed of the motor is 60 radians per second. Okay, so they want us to calculate the, we want to know the magnitude of reference voltage. Okay, so we want to calculate the magnitude of reference voltage given, all these quantities. Okay, so I'll just write the quantities first of all that have been given to us. Okay, so armature current has been given to us, right? 0.4 ohm, and then the speed EMF constant, it has been given as 0.25, right? Volts per radian per second. And then what are we writing? Okay, so the load essentially is, it's a constant load this time. Okay, so no dependence on angular speed is there. Okay, and so what is the angular speed? It is again given to us 60 radian per second. Also, the source voltage is also given to us this, I mean, and in this case it is 48 volts. Okay, so what we actually need to calculate the magnitude of the reference voltage. Okay, so essentially we need the modulation index, or what we have been calling the duty cycle for this much time. Okay, and whatever is the duty cycle, okay, so the duty cycle multiplied by the peak voltage here. Okay, this gives us the magnitude of reference voltage that we need to provide. Okay, I'll just clean this here. Okay. So essentially what we need is the magnitude of reference voltage. Okay, and how much is the reference voltage? It is equal to the duty cycle, or you can call it, okay, the modulation index multiplied by the peak value of the reference signal. Okay, and the peak value of the reference signal, okay, or the amplitude is given to us as 10 volts, right? So we just need to calculate the modulation index. And how do you calculate the modulation index? If I have my armature voltage and I divide it by my source voltage, I get the modulation index. No problems there. Okay, and how do I calculate my armature voltage? I know from the last two questions that, I mean, how do I calculate? I write the speed torque relation of the motor. Okay, and what is the speed torque relation? This is my armature voltage minus Ra, that is my armature resistance, times the torque over K squared. Okay, so we put everything here, we will get K. No, we don't. We already have K. Okay, we will get our armature voltage as 15.64 volts. Okay, and how do we calculate our, duty factor or modulation index? We calculate like this: armature voltage divided by the source voltage. Okay, so 15.64 that we have calculated just now divided by 48 volts we have been given. This comes out as 0.3258. Okay, and now once we have this modulation index, we can easily calculate our VREF like this. Okay, so what is your VREF? VREF is your modulation index multiplied by, you know, peak voltage or the amplitude of the PWM signal. Okay, and in this case it is 0.3258 is our modulation index and 10 volts is our amplitude of the PWM signal. Okay, so this comes out to be 3.258 volts. Okay, this is the reference voltage that I would set, in my microcontroller to get a modulation index that gives me an armature voltage of 15.64, like give me an armature voltage that rotates this motor at this power, okay, at the given power. Okay, like this is how we go in the inverse direction for this problem. So I guess this is enough for this week's lecture. Okay, like this is all you guys. Oh, and also I should. So we've been given the construction of the H bridge here, right? Okay, I'll draw it in the form of a transistor since you might have seen it that way only. But you can, these are just switches. So essentially, I've drawn these four transistors here. Okay, and transistors are being used here just as switches. Okay, and these are the terminals where we give our input signal. Okay, to control motor. Okay, this is your source, and this is your ground. Okay, and your motor is connected through these terminals. Okay, and according to the numbering scheme given in the problem, okay, this is what we, this is how we number, how we have numbered according to the question, all the switches in this H bridge. Okay, this is what we call an H bridge. Okay, so it is as given in the question, and you have seen it in the theory also. We never operate the switches on the same leg, at the same time. Okay, otherwise we are just shorting our source at the ground. Okay, essentially we're just shorting our source. Like, let's say it's the battery or a voltage supply. Okay, so we have been given that 1 and 2. Okay, we should use a different colored pen here. Okay, so use I operate 1 and 2 simultaneously, and 3 and 4 simultaneously. Okay, I never operate 1 and 4, or 2 and 3, because again it will just short my source. So now here in the H bridge we give PWM signals to these gates. Okay, so we give PWM signals to you know make this switch on or off. Okay, and the speed, or essentially the time for which it is on for a given switching time, okay, or a given time for the PWM signal, okay, that is been given here. Okay, for that particular time, okay, we get our essentially the modulated voltage here that is supplied to the motor. Okay, this is what is your H bridge looks like. Okay, so we are just calculating that what is the reference voltage we should give to our timer circuit, so that, okay, we get a modulation index, okay, of so that we get a modulation index that causes, okay, a particular armature current that runs our motor at 60 rpm at a constant load of zero point 0.4 newton meter. Okay, this is what we want. Okay, so I guess this much is enough for this lecture. um, Thank you.